Okay, that's versus VS. V. Versus, you know VS like Ireland versus.
Oh.
Yeah. Like
games.
Games, yeah. VS. Current versus voltage. Or you could say current against voltage. Right. So yours looks fine and yours looks fine. And I don't know, maybe yours is fine. Okay, so I'm not going to think about that again. I'm just going to think about the type report now. Okay, so the next things I want to see will be the electricity and the Newton type report. When did I say? We have a look on Thursday? Did I say Thursday? Yeah. We'll have a look at what you've done by Thursday. Is that the door? Door? Did you lock the door? Hey, can you? No. Yeah. Alright, so we'll start then. Good job on the journals, but remember, they're only 2%.
Journal?
Yeah, that's only 2%. That the type report is 18%. Big deal. Okay. So we have no homework to do, so we'll start a new chapter. Okay. Well, look who made it. Did you hand in your report? And what did you give to Joan as your reason for being a day late?
No, I thought it was a draft.
Hareen.
Because
Hareen.
I'm not paying this for you grades, but this was the final draft. I didn't know final draft meant the actual assignment. I thought it was just the final time you can check.
Oh, Hareen. Classic Hareen mistake. Right, okay. Well, anyways, I was just looking at the journals. So we'll start the final chapter.
Yes.
Exciting.
But not interesting.
No, I think interesting. Do you like chemistry? Yes, then it is interesting.
Tomorrow we have 3 hours chemistry afternoon.
You have how much?
3 hours.
Yeah, exciting.
3 hours?
Yeah.
Tomorrow. Tomorrow is Wednesday.
No, we
3
have
actually.
3 hours every Thursday.
Yeah.
Tomorrow is Wednesday.
What?
Today is
No,
Tuesday.
Thursday. For example.
Hareen, can you move this to the right a little bit? More? There. Okay, great. You normally have 3 hours of chemistry?
Oh, Thursday. Normally 2 hours and go home.
Yeah, sounds nice. Okay, here we go. Is this the right lesson? Come on, come back. Yeah. The blind's broken, but I think we can see okay. So, like I said, yeah, I don't know who pulled it down. One of the business students maybe. What was I saying? Oh yeah, so last chapter, what are we going to look at? It'll load in a second. So you've all done a little bit of atoms with Lorraine. You have some basic vocabulary, yeah? You know the names of the names for the parts of the atom inside. So what are the 3 parts of the atom?
The
proton, electron, and neutron. And we know these words from physics. Which is positive? And negative? electron, and no charge, neutron. Which are the bigger ones?
The protons and the neutrons.
Proton and neutron and electron is the smallest one. Yeah? And you've also done, you've also talked about orbits as well, haven't you? And we'll talk a little bit about orbits as well. Okay. But before all that, the lesson title. Nuclear decay. Okay. You got that title? Yeah? Right, so maybe you heard this word before from TV shows or movies. Radioactive. You want to think of things like the Hulk, what else now? Fantastic Four. What else now featured radioactivity? The Hulk, you know the Hulk? Fantastic Four.
Yeah.
What else?
Isn't that it?
I know.
Iron Man, like.
Right, I guess, yeah. So radioactive decay, also known as nuclear decay, or radioactivity, the loosened names, is the process by which a nucleus of an unstable atom loses energy by emitting radiation. The types of radiation are alpha, beta, gamma. Okay. You got that? Yeah? Continue now? Okay. So, an example would be something like uranium 239. This is an isotope. You know this word from chemistry? Isotope. It's radioactive. This means it will decay. This means that alpha, beta and gamma radiation will come from it. So if this is uranium, you have alpha, beta and gamma, they come out from it, and of course that's dangerous. And note that it will not do this forever, so it'll do it for some time and then it stops. More about that later. Okay, so there are three types of radiation. The first is alpha radiation. Alpha radiation is actually just a 2 proton, 2 neutron atom molecule. So that's all it is, 2 protons and 2 neutrons, which makes it helium. So alpha is really the same thing as a helium, 2 proton, 2 neutron. No, just that radioactive material would release alpha particles. this? No? Okay. So, if alpha has 2 protons and 2 neutrons, what is its charge?
2 plus.
Yeah, plus 2, because it has no electrons. So its charge is plus 2. Okay. The symbol is alpha, or just helium-42. Okay, got that? Yes? Right, now, beta particles are high energy, high speed electrons. That's all a beta particle is. The symbol is beta, or E written like this, 0 minus 1.
What is high speed?
A beta particle is just a very fast electron. That's all it is. Yep, that's all. Nothing special. Okay, do you have this? Sleepy. Everybody's sleepy. I want to be at home watching TV. Okay, you have this? It's so sleepy because the weather's so heavy.
Heavy?
Heavy, feels heavy. Yeah. Okay, so the next one is gamma. So gamma rays are high energy electromagnetic waves. The symbol is gamma. Gamma radiation is very important because I believe it's what gives the Hulk its superpowers. Am I right, or maybe gamma? Yeah.
I didn't.
Okay, I think it's gamma.
So what about the American capital? Is it the same or different experiment?
No.
Which one?
The American.
Captain America?
Yeah.
Oh, I don't think his is radiation.
Something.
I think his is just a drug.
Drug something.
Just drugs, yeah.
Make it stronger.
Yeah, that's
And
all.
I remember some friends said the Captain America is just like skill something skill, so it's not the real exercise. It's not like a hero. I think.
Yeah, he's a cheater. He uses drugs.
But Batman isn't as well, right?
Batman doesn't use.
Just has
Batman doesn't use drugs. All right.
Just rich.
That's it. Yeah. Yeah.
It's important.
That's very important. Okay, you got this? Yep. Right, so Newton's first law tells us that the atom should not just decay. That is, a force must be acting. So, for example, if I just go here, what's happening is you have, let's draw them here, proton, neutron, proton, neutron, neutron, etc. So if an alpha particle comes off, and alpha is, remember, 2 protons and 2 neutrons, Newton's first law says an object should remain at rest unless there's a force. So because, where's it gone? Yeah. Because this left, there must have been some force that pushed it out. Do you understand? It didn't just move by itself. There was some force that pushed it out. So what is the force that pushes out alpha and beta? Well, that force is called the weak nuclear force. The weak nuclear force is a weak repulsive force, that means like pushing force, which acts only in the nucleus of an atom over a very short distance, 10 to the minus 18 meters. So all this force does is just pushes the radiation out, and that's all. And it's only for a very short distance.
And then how does it like go out?
Well, once the atom is in motion, then again from Newton's first law, it would stay in motion unless another force stops it. So it is the force responsible for nuclear decay. Okay. Continue. Has anybody ever heard of this force before, the weak nuclear force? No. I don't think you do it in chemistry then. Do you do radiation in chemistry?
I think it's the last chapter.
Last chapter maybe? Okay. You might wonder if there's some counterbalancing force. So if there's a force that pushes out, is there a force that pulls in? What do you think? This weak nuclear force pushes out. Do you think there's a force that pulls in? Yeah, there is. And we'll look at that later. Okay. Now, the next slide, I hope I use the same words as Lorraine. So, proton number, I think you know what that is. What's the proton number?
The quantum number, the number of protons.
Yes. It's the number of protons. What do you call it?
Atomic mass number.
No, it's not atomic mass number. Maybe atomic number. What do you call it in chemistry?
I think the mass number is the whole thing.
It's the whole thing, which is not this. This is the proton number.
Atomic number.
Atomic number, maybe. This defines what the atom is. For example, one proton makes... What does one proton make?
One positive.
Yeah, no, what's one proton called?
Hydrogen.
Hydrogen. Yes? Two protons make helium, etc. And where can we get this information? Periodic table. Okay, ready? No? Ready? Good. Okay. So, do you use this with Lorraine? Nucleon number?
No,
Now, what do you think it is?
the number, the whole thing, the mass number.
Yeah, you have two ideas. So you think the number of neutrons, and you think the total number of neutrons and protons. But maybe you think about this. You have, what's the center called?
Nucleus.
The nucleus. And what's in the nucleus? The nucleons. Yeah, the protons and the neutrons. So this is just the total protons and neutrons. Note that normally the number of protons and neutrons are the same, but not always. So for example, if you have 2 protons, then you usually have 2 neutrons, but not always. If you have more neutrons, then you have a isotope.
Should we remember the definition?
For the exam, they do ask it, yes. But it's easy. It's just the number of protons and neutrons. So you wouldn't even, for the exam you would just need the first sentence. Maybe I shouldn't have this in the box. Maybe I should put it underneath. Okay, continue. Yeah. Yeah, yeah. Oops. Okay. Okay, continue. Yeah. So, the atom of a chemical can exist in different types. These are called isotopes. They have the same number of protons and electrons, but a different number of neutrons. Different isotopes of the same element have different masses. So for example, this is hydrogen. It has 1 proton. Oh, actually I forgot. I didn't say this because I'm sure you know this from chemistry. I should say it now actually. This number at the bottom is how many protons, and the number on the top? The nucleon number, the protons and the neutrons. So here, this has 1 proton and no neutrons. This one here has 1 proton and 1 neutron, and this has 1 proton, 2 neutrons. So which is the right one, so to speak? This one is the normal one, because it has 1 proton and 1 neutron. This hydrogen.
Hydrogen has no
No, but what I'm saying is, this is all hydrogen, but it's different number of neutrons. So these are all isotopes. So what I'm saying is, if you have 1 proton, you expect to have 1 neutron. And here is 0, 1 and 2 neutrons. And these are all hydrogen. However, these you're right, sorry, hydrogen is a bit weird because it normally only has 1 proton and no neutron. Maybe this is a bad example. Anyway, hydrogen 2 and hydrogen 3 are isotopes of hydrogen since they have more than 1 neutron. Did I say that right? No, that's stupid. Just stop at that. So, oh sorry, you need this. Okay, you got this? No. Let me just check my battery. Battery is okay. Okay, continue. So let me just fix this. And I didn't say it, but I'll just write it here. I mean, you all know this from basic chemistry. What goes here? This is the proton number. And then what goes here? Let me write as an X. Proton number and nucleon number. So in this atom, how many protons does it have? It would be Z, yeah. How many neutrons? A. No, it should be Z. Oh, sorry, I'm being stupid. A minus Z. Yeah. And if it's balanced, how many electrons should it have? Should have Z. Now, if I write a plus here, do you do this in chemistry? Yeah, it's an ion, and it'll have one extra or one less?
One less.
Very good. And if I wrote a minus here, it would have one extra, yeah. And do you do it like this, plus 2? Yeah, okay, good. Yeah. So sometimes you might have a plus or a minus here, which will change this. So I'll put in here plus extra. And there might be extra information here. Yeah. And then, what does it mean if I have a 2 or something here? Yeah, like if I wrote H2, what does that mean? 2 hydrogen bonded together though. Yeah. So this one here tells us something about the bonds. Yeah? Okay. But I mean, this is stuff you know from chemistry. I hope. Lorraine will be very angry if you didn't know this. I think very angry. Okay. Right. So alpha, beta and gamma, they have different abilities to penetrate. So for example here, you can see alpha particles. Look at me. Look. Alpha particles, you can stop them with your hand. Okay, so if there was alpha coming from this, you could block it with your hand. Okay. It wouldn't be great for your hand. I wouldn't do this often. Beta will go through your hand. You would need something like aluminium to stop it. You know aluminium? And gamma will go through your hand and it will go through aluminium. and you can only stop it with lead, big wall of lead or concrete. You asked me this before. Lead is like what's in the old pencils.
How
Yeah?
Okay, easy.
Yeah, it's okay.
how thick does the aluminium have to be? Can aluminium foil stop?
I don't actually think it needs to be that thick. I don't know if regular kitchen foil would be strong enough. It's more like a sheet of aluminium, like maybe I don't know, like maybe a 1 centimeter sheet of aluminium, like in a building or something, you know, in a car or something should do it. I don't think a piece of tin foil would do it. I'm sorry. So sometimes they ask you to draw or describe the penetrating power of alpha, beta, gamma. So you can draw the picture or write it down in your book. Go ahead. Okay, you got that? Are you drawing? Let's see. Great. Who are you talking to, Andy? Who are you talking to? Who?
My girlfriend.
Oh, interesting. Is she not in class? Tut tut tut. Let's see what must. Let me send a message. I have a delivery. I need to tell my wife to pick it up. Oh my goodness, I can't type. I ordered something for my birthday.
Oh.
I ordered a scooter. You know the ones you
I thought
with your foot.
What
No.
was your birthday?
It was last week. You missed it. You missed it. Got me nothing. Yeah, that's something I suppose.
How did you have a birthday?
Because she's a good student. She hands her assignments in on time. She does her lab book. Alright, continue. I'll show you a picture of it later. You can see me. I'm going to take it to school. It takes so long on the bus.
So you're gonna ride a scooter to school?
From the city centre. This is my plan. as long as it doesn't kill me.
Big one or
No, a small one that you fold up.
small one, you can stand it up and just go.
Yep, yep.
Ooh.
And you can fold it up, you know, so you can take it on the bus.
How lazier.
Bicycle?
Yeah. Yeah. No, because the bicycle is too big for the bus.
Yeah, affordable bicycle.
Oh no, they're stupid. They're stupid. Yeah. No, but they're no good. They're no good. Okay. Let's look in more detail what... Oh, I already said this, so we know what this means. During radioactive decay, there are 4 quantities which are conserved. So what I mean by that is, if I go back to my picture... Oh. Hold on. Right. So what I mean by that... Try again. Okay. So what I mean by that is you have something here which is radioactive, so I don't know. What did I say at the start? Uranium-239. Huh? I don't remember. What was it? Uranium-236, was it? Uranium-239. So what happens here is the alpha comes off and the beta comes off and the gamma comes off. So there are some things which stay the same. So for example, this is what you have before, and then what you have afterwards, your uranium-239. Here you have alpha, beta and gamma. There's some things which are the same before and after. So for example, here, if this is M1 and this is M2, you know, and this is U1 and this is U2, and here the M2 is kind of inside of it. So I'll draw it here. The M2 is in here and it has a V1, and here's the M2 and it has a, sorry, what am I saying? V1, U2, and this is V1, and here is V2. So you know that from semester 1 that the momentum is conserved, that the momentum here should equal the momentum here. So what I'm saying, oops, the speed of the, the U1 would be the speed of the uranium, and the U2 would be the speed of the alpha, beta, gamma. So at the beginning, they're both at rest. Yeah. Do you remember the example we did with the gun? At the beginning, they're both at rest, and then when the bullet is fired out, what happens to the gun? It goes backwards. And you can calculate this by using this formula. You remember that?
Yeah.
This is because momentum is conserved, that the momentum is the same. This is what you can do. And it's the same with the radiation. So if you have your uranium-239 and it shoots out an alpha, beta, gamma, then what happens to this? Like the gun, it should also move backwards. So what I'm saying here is there are 4 things which are conserved, which stay the same. They are energy. You remember this? The energy at the start equals the energy at the end. What else is conserved? Momentum is conserved. Now what else do you think is conserved? What else do you think is the same at the start and at the end?
Charge.
Say again? Time? No, not this, no. The charge. Yeah, so for example, if you have a total charge of 0 at the start, then your total charge at the end is also 0. Yep. Good question. What's the last one? the nucleon number. So in other words, the last one's a bit difficult to explain. I have to show you with an example. So, well, I wish you were ready. Okay, continue. So by nucleon number, I don't even mean the number of protons, neutrons and electrons necessarily. I'll explain it with an example in a moment. Okay, can I go on? Yes? Right. Simple reaction. So, since alpha is 2 protons and 2 neutrons, then the decaying material will see its number of protons and neutrons decrease both by 2. So I'll give you that as an example. So let's say, I don't know, oh my goodness, do you have your periodic table? Does anyone have their periodic table?
I can search.
Huh? Search uranium. Or open up a periodic table. So uranium 239. I can't remember. I think it's one. I want its proton number. Type in atomic number of uranium. Yeah, it's a U.
I see uranium.
I think it's 130.
Why is it not under this?
Hang on, it does exist.
You can make it bigger.
Uranium, sorry, I was way off. What am I talking about, 130? Uranium is 92.
Wow, 239.
No, the bottom here is 92. Okay, can we look back up?
92?
It's at the bottom.
You mean the
Proton number.
But 92 is niobium.
I just saw it as 92. The proton number, not the mass number.
Wait here, opposite.
Can I continue?
I see it now.
Okay, put the phone down. We look up. It's okay. It doesn't even matter if it's right. It's not important for the next part. Grace. Okay, continue. Okay, so tell me, imagine you have one uranium atom. How many protons does it have? 92. How many nucleons? 239. How many neutrons? 239 minus 92. So, if this releases an alpha particle, how many protons has this lost? It's lost 2. So it doesn't have 92 anymore, it has 90. And how many nucleons has it lost in total? It's lost 4. 2 protons and 2 neutrons. So here shall be 2, 3, 5. Now, is it uranium still?
No.
No, it's not uranium. Why not?
The number.
Because it has 90 protons instead of 92. So it's become something else. I can't remember what it is. Neptunium, maybe. Do you want to look it up? correctly, please?
90 curium.
Oh yeah, sure, yeah. Let's go back. Let's run through that again. So, if it releases an alpha particle, alpha is helium-42. Yep. So, it no longer has 92 protons, now it has only 90, because it gave 2 of them to its alpha particle that it released. And it no longer has 239 nucleons, it now has 235. Yeah? Because it lost 4 nucleons. And is it uranium anymore? It's not.
It's
Thorium. T-H. Now, are we looking, Chris?
Can't find.
That's okay, it doesn't matter, doesn't matter. Now, what I want you to notice here is that 239 equals 235 plus 4. And 92 equals 90 plus 2. So back at the slides, when I said the nucleon number is conserved, well, it's not just the nucleon number, but also the proton number as well. This equals this plus this. And also, this equals this plus this. That the totals at the top and the bottom stay the same. Yeah. Now, beta particles are strange. Since beta is 1 electron, then the decaying material will see its number of electrons decrease by 1. So, if a beta is released, what happens to the atom? It loses 1 electron. That makes sense, doesn't it? Yes? And something else very strange happens. Ready for this? No, you're not ready, okay. Just get ready. And oddly, 1 neutron will become 1 proton. Just like that. So one of the neutrons will turn into a proton.
Wow.
Yeah, these are all very good questions which will not be answered on this course. So, not only does an electron is released, but one of the neutrons becomes a proton as well. You might ask, how does a neutron become a proton? These are all good questions which will go unanswered. Yes. So, for example, here, if the... Where's my pen gone? Oh, it's broken again. Go on, do. So, if it releases an electron, I know it's a bit messed up. If one of the neutrons becomes a proton, then what happens to the number here? Is it 92 anymore? No, it's 93. One of the neutrons becomes a proton. What about the nucleon number? No, it's still the same. Because if 1 proton becomes 1 neutron, there's still the same number of nucleons in the nucleus. Is it uranium still? No. Would you be so kind? Thank you. Let me fix my keyboard.
It is
Yeah, what is it?
Neptunium.
Oh, my stupid pad. Neptunium.
Oh wait, 93, right?
Yeah.
Neptunium.
NP.
Yeah.
I will. The,
Why is the same?
which is the same?
239.
Oh yeah, because here there's 92 protons and 239 minus 92 neutrons. If you get an extra proton...
That's an Einsteinian.
Yeah, there is, yeah. If one of the protons changes into a neutron, the total number of proton and neutrons are the same. For example, if one of the boys here change into a girl, there's still the same number of students in the class. So the number of students hasn't changed, but the number of boys has changed. Yeah? Alright. Oh, come on! There we go. The proton increases, one of the neutrons becomes a proton. Yeah. So to keep it balanced, we say that there's a 0 here, there's no protons and there's no neutrons. But for the equation we write a -1 here. So this is what a beta looks like. Okay, continue. Right. So that's strange, isn't it? And please ask Lorraine. It's too difficult for this class. Maybe you can do it in chemistry. But I think she will just tell you to ask me. I know it's weird, but it happens during beta decay. Anyways, for gamma, no particles are released, so nothing changes here. Gamma is just a wave. So for gamma, the protons and the neutrons and the electrons, they don't change their number. It's just a wave that's released. So gamma is fine. When a radioactive material decays, we can represent this in an equation, like what you do in chemistry. So you do reactions in chemistry, don't you? And bonds and reactions and things like this. So we can do something similar in physics as well. We have an equation to balance. Okay, so let's have a look at an example, I think. So I have, let me see, I have 2 examples to look at. Okay. So the first one, write this down, please. We only have 2 examples to do, so there's lots of time. So you can write all of this down. Now there's, wait, before I write down, I left out a word. Wait, stop! I wanted to say undergoing radioactive decay, and you can put in brackets alpha decay. I mean, you don't have to, but in this example I was looking at alpha, and then I'll look at beta. Correct. Do you like learning about atoms in chemistry?
No.
Of course you do.
How do we not like it? That's all what chemistry is about.
Of course. Okay. No. Okay. Okay, ready? Now. So the first one, I actually have done it already for you. If you have uranium 239 and 92 and it releases an alpha, then what you must have here is 235 and 90 and thorium. So that's the answer for the first part.
But if we don't know what is the proton,
You need your periodic table.
in the exam,
No, they'll tell you in the exam. Okay. Is that okay? B. What's the next part? What's the recall velocity of the alpha particle? Yeah. When its speed is 0.05 c. So what happens is, at the beginning you have uranium 239. So when you look at it, if you picture it like this, you have your uranium and you have your alpha together, and that's an M1 and that's an M2. And then later they split into thorium and helium, and that's an M1 and that's an M2. And this is a V1 and this is a V2. Okay, so we have M1, M2, U1, U2, V1, V2. Come back. There we go. No, one more time. One more time. One more time. Well, there we go. Right, we have M1, M2, U1, U2. Well, I know they're 0. And B1, I don't know. And B2, I don't know. Do I know what M1 is? No. What is M1? Well, it's actually the thorium that's inside here. I should really say maybe thorium. When they're stuck together, they make uranium. Do I know what the mass of thorium is? Not really. I know how many protons and neutrons does it have? 235. So I know its mass would be 235 times whatever the mass of a nucleon is. Would be a small number, but I don't know what that is. But in fact, I don't need to know it. What will be the mass of the alpha? 4 nucleons. I don't actually need to know what the mass. Yeah. Say again. The mass of a nucleon, a proton or a neutron. A small mass. Okay? So you have M1U1 plus M2U2 equals M1 V1 plus M2 V2. So I have 235V1 plus 4V2 equals 0. What am I looking for? I forget. And I also tell you that the velocity of the alpha particle is 0.05 c. So I tell you that the V2 is 0.05 c. So that means V1 will equal minus 4 times 0.05 times 3 times 10 to the 8 all over 235. Can you calculate, please? Thank you. You got your calculator, Sophie? And Hareen? Oh yeah, what you mean here, is it? Yeah, the formula I'm using is M1U1 plus M2U2 equals M1V1 plus M2V2. You know this formula? Yeah. So this is M1V1 M2V2, and this is M1U1 M2U2.
Minus?
It should be minus, it's going left.
Minus 2.
You look confused.
And why, at the first step, why M1 and M2 multiply?
Here, is it?
No.
Here. Oh, here.
Yeah.
Well, because thorium is 239 protons and neutrons. So what I'm saying is the mass will be 239 times the mass of a proton or a neutron. Now I don't know what this is. It's on my calculator. I don't know what it is. So I just called it delta M, because I knew that I don't need to know it, because I can cancel it. Are you sure? I don't know if I believe you. If you're just being nice to me and saying, okay. My notes here? Oh, these are just scribbly, messy notes. What did you get, Grace? Minus 255,319. Sure. Okay, that's bigger than I thought. 255,319 point. So just this then.
Do we have to put the negative?
No.
Oh, visual speed is normal meter.
Oh, no, you can leave with meters. Can I go back, Sophie? Yeah. Okay, you got this? Yes? Okay. So, oops. What is the velocity if it was a beta particle? So for the next part, beta particle, it's nearly the same. Can somebody tell me the difference if it was a beta particle? Well, okay, let's do it. So we start off with uranium 92-239, and then we have our, it becomes neptunium 93-239 plus 0 minus 1. So M1 M2 no, delete this question. I don't like it anymore. I realize it's silly. Right. And we'll delete the last part. So there's only one part left for A. I'm only delete C and E. We'll just do alpha, not beta. Right, so the last part now is what's the energy of the alpha particle? So can somebody tell me what type of energy the alpha particle will have? What do you think?
Ionization energy.
No.
Oh, kinetic energy.
It'll have kinetic energy, won't it? The alpha particle will have kinetic energy. So let's calculate it. The energy of the alpha particle will equal the kinetic energy of the alpha particle, which will equal a half mv2 squared, which is a half 4 delta m times 0.05 squared, which is a half times 4, there's a C here as well, 0.05 times 3 times 10 to the 8 squared. I'll write that bit again here. C, close. Speed of light. Yeah. So what's the only thing I'm missing in this formula? Wait, slow down, Hareen. What's the only thing I'm missing in the formula?
Mass of electron.
No. Mass of...
Proton. Yes.
Mass of proton and neutron. Now, in fact, the mass of the proton and the neutron is nearly the same. And if you look, it's on your calculator. Can you see it's constant number 1 and constant number 2 is the proton and the neutron. Can you see that? One and 2 are proton and neutron. So what you can do, let me just get rid of this 4 here. How many protons do we have? 2. And how many neutrons do we have? 2. So using your calculator you can get this. Tell me what you get, please. Because here it was 4 protons and neutrons, and I changed it into this, 2 protons plus 2 neutrons. Oh, you all have the new calculator. Nice. 7.532
multiply 10 to the power minus 13.
13. Oh, let me think. Minus 6 is micro, minus 9 is nano, minus 12 is piku, like Pikachu. Minus 12 is piku. So hang on, let me see. This is 7.53 times 10 to the minus 1 times 10 to the minus 12 joules. So this is piku. Do I want piku? And then after piku is what? It's okay, you don't need to. I just like to remember. You can keep your answer like this. Oh my goodness, I don't know what you're talking about. Good.
Because Piku means light.
Great, that's great. You're confusing me now. 753 femtojoules, I think. I think.
So I think it's true.
Yes, do.
5 suddenly become minus. Oh, yes.
Continue. I think it's femto. Makes it easier, huh? Okay, next and last example. What? What? Yeah.
Large.
Which of course you know means it's long to do. Half a page maybe. I think that's enough space. Yeah. Yeah? Okay. Let's have a look. So, right, so what do we start with? Uranium, is it?
Yeah.
Uranium 239? 235 and 92. And what does it become?
20782 lead.
PB. And this process produced alpha particles and it produced beta particles. Do we know how many alpha and beta particles it made? No, we don't. That's what we want to know. So let's say it produced X alpha particles. What's alpha? 4, oh my pen again. 4, 2, even my laptop is sleepy. Come on. Wake up, there. Great. X42 helium plus Y minus 10 electron. So this is X alphas and Y betas. We don't know how many alpha and betas. Now, before I continue, I want to make sure this is okay. Is it okay? So, how many nucleons do we have on the left? 2, 3, 5. Yes? we don't know how many heliums we have. X heliums. Okay. How many nucleons do we have here? The first one, lead. Come on. 207. Now, how many do we have here?
4.
No.
4x.
4x, because we have x of them. And how many do we have here? 0 y. 0, yeah. How many protons do we have? 92. How many protons do we have? 82. And here, 2x, and here, minus 1y. So you can change this into 4x plus 0y equals 28. And here you can change it into 2x minus 1y equals 10. Can you solve this? Yeah, if you don't, you'll make Joan and Roland and Stephen very sad. So here, x equals 7 and y equals 4. So the answer is, I'll write it on the top, this becomes lead with 7 alpha particles and 4 beta particles. You'll get 7 alpha and 4 beta. In chemistry, you have to do something like this. What's it called in chemistry? Does anyone know? Remember? Oh, come on, somebody, please. Grace, what's this called in chemistry when you do something like this in chemistry, when you compare the left and the right? Thank you. See, I knew you knew. Balance the equation. Is it as difficult or the same or easier than chemistry, this type?
Easier.
This one is easier than chemistry?
I don't know.
Same? It's for you, right?
Yeah. How to type equation?
What type of equation? This type?
Yeah.
I think this is, let me see, mode, let me see. Yeah. Mode 51. Here, come here, let me show you. I'll show you. Mode 51. So you can type 4, 0, 28. 4, 28, and then 2, minus 1, 10. Ooh, powerful.
So, like at the end, we're supposed to rewrite the equation, but with the x and y variables. Right?
Huh?
In the end, we have to rewrite the equation with the x.
Oh yeah, I mean, here, Irene, this will be an acceptable answer at the end. What? Mode 51.
Oh, what is
X, Y, Z.
what is the and X and
For the Z. You don't need it. Okay, continue. Are you, Grace, show Sophie. Yeah.
What should go back to original?
Comp or mode 1 maybe. Try mode 1.
Ah, yes.
Yeah. Yeah. Okay. Continue. What you got? What are you eating? Oreos, huh? Okay. Right.
No.
Get ready.
No.
Be strong.
No.
Maybe a little or too much?
Too much.
Oh, calm down. Calm down. You can start them now. I want you to start them now.
That's a bad question.
I know you want to kill me.
Now let me explain with an example. Look. Watch. Here, what's this? Uranium-238 plus, what one's this, do you think? What is this? This one? No. How many protons does it have?
0.
How many neutrons does it have? So it is a neutron.
But then how can it just release a neutron?
No, it doesn't. What happens here is you put a neutron and uranium together. So what do you get here? 239 and 92. And is it still uranium? Yeah. So what happens when you put these together, you get uranium plus a gamma. The energy from the gamma comes from the kinetic energy of the neutron. What happens here is, let me try, this is like the uranium, it's big, and then you need something like small, like the key here, this is the neutron. So the neutron is fired at the uranium and sticks to it. Is it still uranium? Yeah. But the kinetic energy from the neutron, when it hits the uranium, it gets turned into gamma radiation. That's what happens. Do you understand that? Yeah? Yeah. So, if you want to know how much gamma energy you get, what should that equal? What should it be the same as? It should be the same as the kinetic energy coming in. The kinetic energy that comes in equals the gamma energy that comes out. Roughly. Anyways, that's easy. Now here, look at this one for example. So on the top, what do you have here? How many nucleons? Great!
Yes.
How many nucleons do you have in this example? 64. How many do you have here? 2. So what should be here? 62. 62. Yeah. How many protons here? 29. How many here? 0. So how many here? 29. This is quick to do. Okay. So you have 10 minutes left. I think you can finish these in 10 minutes, and then you have no homework. Yeah. So try and get these done in 10 minutes then.
After finish and no homework.
Yeah, it's good.
Liar.
What are you talking about?